Hello and welcome. Today we continue with thermodynamics and we're doing chapter 20, heat and the first law of thermodynamics. After this chapter we need to be able to define a number of concepts. These concepts are heat, heat capacity, specific heat capacity, and latent heat. We're going to discuss the relations between heat and work. We need to be able to state the first law of thermodynamics and understand its application. Then we're going to derive the basic law of heat conduction, and we're going to, of course, solve problems on the above. Heat and internal energy. The terms heat and internal energy are often incorrectly used in popular language. That's to say, when we're using these terms in our physics, they have very specific meanings. So we need to be very clear about what the meaning is, and we need to take careful note of the definitions. The definition of internal energy is all the energy of a system that is associated with its microscopic components, so with its atoms and molecules, when viewed from a reference frame at rest with respect to the center of mass of the system. The second part of the sentence just means that if we have an object, flying through space at some speed, then we don't take its kinetic energy into account when we discuss internal energy. We're more referring to the microscopic components and the energy as a result of the atoms and molecules. Here you can see some the sources of internal energy. They include things like the kinetic energy of random motion of the molecules, of the molecules or the atoms rotating, vibrating, and so forth. A second definition is heat. Heat is defined as the process of transferring energy across the boundary of a system because of a temperature difference between the system and the surroundings. So under those conditions we refer to heating something. We transferring energy because of a changing difference in temperature. The second way we use the word heat is also the amount of energy, Q, transferred by this process. The second definition, heat capacity of a system, is the amount of heat in joules that is required to raise the temperature of the system by 1 degree Kelvin or 1 degree Celsius. So this is the heat capacity. You remember previously we spoke how increasing the temperature by 1 degree Kelvin also results in a temperature increase by 1 degree Celsius. When a substance has thermal energy transferred to it, two things can occur. Either the temperature can change or the phase can change. Think about the water in this pot. It's been heated up by this flame around it, so thermal energy is being transferred from the fire to the water, and perhaps the water started at 25 degrees Celsius. As we apply more energy through the fire, the temperature of the water will at first increase, right? So that's the example of the first thing happening. And an example of the second thing happening, a phase change, is when the water reaches a temperature of 100 degrees Celsius. Then what's going to happen is it's going to start boiling and steam is going to be produced. So we're going to be having a phase change. It's an example of the second thing. You need to note that heat and temperature are not the same thing. This refers back to very precise use of the words in physics. When we're speaking about heat, we're speaking about energy transfer due to temperature difference, and it is measured in joules. So the amount of heat, the heat would be the number of joules transferred from the fire to the water. As we're going to see, these are the equations that apply to each of the two cases. The first process then is that of temperature change. The relationship between the specific heat, Q, and the temperature is given by Q is equal to mc delta T, where m is the mass of the substance, c is the specific heat capacity, which is a constant related to that substance, and delta T is the change in temperature. Here we have the definition of the specific heat capacity. This is C over here. Some text may use a capital C. It refers to the same thing. The specific heat capacity is the amount of heat in joules required to increase the temperature of 1 kilogram of a particular substance by 1 degree Kelvin. For example, for ice, the specific heat capacity of ice is 20722 joules per kilogram per degrees Kelvin at 5 degrees Celsius. The second process that we spoke about is phase change. We spoke about how once the water heats up and starts boiling, the phase changes from water to steam. Here, the amount of heat involved in that process to cause phase change is given by Q is equal to mL, where m is the mass and L is the latent heat of the phase change. The word latent means hidden. We can have a number of different phase changes. We can have a phase change of vaporization, and this is the energy that's required to cause a phase change from liquid to vapor. This is the one we have already spoken about in the case of water, liquid water boiling and becoming a steam. We can also have latent heat of fusion, and fusion refers to the process where the change is from a solid to a liquid. So it refers to, for example, an ice block melting. We go from a solid to a liquid. In this case, for L, we would use LF, the latent heat of fusion. Another process we can have is a sublimation, and sublimation occurs when the phase change is straight from a solid to a vapor. So it skips the liquid phase. So be aware that we have different processes of phase change, and accordingly we need to use the appropriate latent heat of phase change constant, either LF, LV or LS. We're going to be doing some calculations, so let's have a look at how we're going to approach those. So we're going to consider two objects in thermal contact with each other, and such that they can exchange thermal energy. And if you have a hot object and a cold object, then they're going to exchange thermal energy, they're going to exchange heat until they reach the same temperature, so until they're in thermal equilibrium and at the same temperature. So let's first have a look at the simple case where we have no phase change occurring. So the following equation applies. You know, the heat gained by object 1 will be equal to the heat lost by object 2. So this is essentially a conservation law. We can rearrange this bring this to the other side, and then we have the sum of the heats, Q1 plus Q2 plus Q3, depending how many objects we had, all the way up to Qn for n objects, would be equal to 0. And we have this conservation law. If there's no phase change, then we know that each of these Q terms, each of the heat terms, will be given by mc delta T. This is the relevant equation to convert between heat and temperature. Remember, each of the different objects would have a different C value depending on their specific heat properties. If we continue then to look at the expression for the simple case of no phase change and two objects in equilibrium, we can use that expression from before to use mc delta T. Substituting into the equation, we arrive at this, where the masses m are the masses of the relevant objects, and the value C are their specific heat capacities. T objects 1R and T object 2R are the initial temperatures, and TF is the final temperature. Note that the two objects will reach thermal equilibrium by the end of the experiment, or just leaving them. They will both arrive at the same temperature, and for this reason, for each of the objects, they have the same final temperature, TF. If we would like to know what that final temperature is, we can rearrange the equation and make TF the subject of the equation, and we arrive at this expression here. We look now at the slightly more complicated case where we have thermal equilibrium with a phase change. And the example that we have in is a glass of water in which we have some ice cubes at 0 degrees Celsius. As it says here, some of the ice will melt, and then we'll have a mixture of melted water that will mix with the original water, and it will reach some thermal equilibrium, so some final temperatures. Again, we need to take the same equation as before, that the sum of the heat of the object is 0 for all the objects for conservation of heat, and we need to add in the term for the latent heat of the phase change. So these are the terms that we would have had before. Q is equal to mc delta T for the water and for the ice, and then we include this term mf, the latent heat of fusion, for the phase change of the ice. This is for the ice melting and becoming water. This will be a little bit clearer when we do an example towards the end of the chapter. The first law of thermodynamics, it's a conservation law, and it deals with the change in internal energy of a system. It says that the change in internal energy of a system is equal to Q plus W, where Q is the heat added to or removed from the system, and W is the work done on or done by the system. For Q and W, we need to take care of the signs that we use. For example, if we speak about the work, and we speak about work being done on a system, if work is done on a system, it will increase the internal energy, so we will use a plus sign for W. If work is done by the system, then the energy will decrease of that system, and we will use a minus sign for W. Similarly, we need to take care of the sign that we use for Q. Depending on if heat is added to the system, then we would use a plus sign. If it's removed from the system, we would use a minus sign for Q. Let's take a look then at an example. An aluminium can, the mass of the can is 500 grams, contains 117.5 grams of alcohol at 20 degrees Celsius. A 200 gram block of iron at 75 degrees Celsius is dropped into the can. What is the final temperature of the alcohol? We're given this heat capacities of the alcohol, the iron, and the aluminium. Note these are in joules per kilogram per degree Celsius. So the temperatures I'm going to be using are going to be in degrees Celsius. It's useful to start the problem with a diagram, and the diagrams as shown. We have our aluminium can. It's given its mass. We given its initial temperature is 20 degrees. The same initial temperature as the alcohol and the mass of alcohol we have. Note we working in kilograms, converted the masses to kilograms to SI units. And similarly, we're given information that the iron bar initially has a temperature of 75 degrees and weighs 200 grams, so 0.2 kilograms. Whenever we do these types of problems, we need to have a clear drawing and identify each and every object in the question. We need to have the beaker, it's an aluminium can. We need to have the alcohol and the bar in this case. Note that what's going to happen is this aluminium bar, it's a lot hotter than the can and the alcohol, right? So it's going to heat up both the alcohol and the can. And at the end of the, after some time has passed, everything's going to reach thermal equilibrium, and the aluminium can, the iron bar, and the alcohol, they're all going to have the same final temperature, which I've called TF. At the end, all objects will have the same final temperature, TF. So the way we do this problem is we note that it's a simple problem where we just have temperature changes. We don't have any phase changes. So we can use our conservation law to say that the sum of the heats of each of the individual objects, of the iron bar, of the aluminium can, plus the alcohol is going to be 0, the conservation law. Then because it's we have change in temperature occurring, we use the formula MC delta T for each of them. Of course, we need to be very careful to specify which object we're referring to. So for the iron bar, I've used the subscript Fe. That's because the chemical element of iron is Fe. So we need to use the mass of the iron. We need to use the specific heat of the iron which we're given, and the change in temperature of the iron. Similarly for the can and the alcohol, we expand its terms. And then we're actually given all the information. We're given the various masses, we're given the values of C for each object, we're given the initial temperature for each of the objects, and the only unknown is TF. This is the final temperature that we solve for. So we then come out to an answer of TF is equal to 26.12 degrees Celsius. The final example we'll deal with in this chapter, it speaks about a camping stove. In a camping stove, 50% of the energy released in burning the fuel goes into heating water in a pot on the stove. If we heat 1 kilogram of water from 20 degrees Celsius to 100 degrees Celsius, and then boil 0.25 kilograms of it away, how much fuel do we burn in the process? Assume that 1 gram of fuel releases 46 kilojoules of energy. So the first thing for us to note in this question is that what we're having is heating. We're heating up some water from 20 degrees to 100 degrees, and then we also boiling some of it off. So this boiling implies that we also have phase change, right? And we approach the problem accordingly. So we approach the problem in a very similar way to the previous problem. We start with a sketch. Initially, I have 1 kg of water. It's at 20 degrees Celsius. For each of the different processes that are occurring, we need to now draw them out in the sketch. So the first process that is occurring, it's a heating process where the water is being heated from 20 degrees Celsius to 100 degrees Celsius. As we've seen, when we have heating taking place, the equation that relates the amount of heat, the amount of energy in joules to the temperature is Q is equal to MC delta T. What happens then is some of the water, it's heated further and it evaporates. So the stove continues heating the water, and this causes some of the water to evaporate and to become steam. And we in fact told that 0.25 kilograms of steam is produced. For this for this evaporation process, the equation that we'll use for the heat is the mass of the steam times the latent heat of vaporization, LV. And from tables, we can see the relevant values of C for the water and LV for the evaporation are these values given here. Note the units in kilogram, degrees Celsius, and kilograms. So then for each of these steps, we can calculate the total energy needed. In this case, we're ignoring the fact that the camping stove only operates at 50% efficiency. We'll consider that at the end. Let's just see the amount of energy needed for this process to occur. So the energy needed then will be the amount of energy needed for step 1 to heat up the water, and for step 2 to convert the water to steam. We need to be careful with the masses that we use, right? Here all of the water is being heated up. Here only 0.25 kilograms is being changed to steam. So M steam is 0.25 kilograms. So the total energy needed is given by this expression here, and we can compute that to be 8.99, nearly 9 times 10 to the 5 joules. Okay, so that's the total heat we need to heat up the water and convert it to steam. Now what we need to deal with the fact, with the other information in the problem, the fact that we asked to calculate how much fuel is needed. We told that 1 gram of fuel releases 46 kgs of energy, and we told that the camping stove only has an efficiency of 50%. So the mass of these are the two facts that we given. I've stated them there. So the mass of the fuel needed is going to be the total energy that we needed. That's the value that we've just calculated here, that we've just calculated up here, divided by the energy produced by 1 gram of fuel, which is this value here. And then we need to multiply it by an efficiency factor. You can think for yourself, since the camping stove burns with a less than 100% efficiency, it's only burning with 50%, we need twice as much fuel to complete this process. So this is the efficiency factor. It takes into account the efficiency of the stove. The efficiency factor is 2, since it's 50% efficiency. Using all this information, then we can compute that the total mass of fuel needed is 39.13 grams. Right then, this problem brings to an end this chapter. In this chapter, we saw that heat has a very specific meaning in terms of energy. We also saw how to deal with heat in terms of 2 different processes. The first process is changing of temperature without phase change. The second process was when phase changes occur. And then, of course, we also dealt with the first law of thermodynamics.